So sorry guys, the last part of the video kind of kicked out on me there, and the audio wasn't going for some weird reason. I'm not sure what happened there. But let me go back over this so you guys can see it. What I wanted to talk about, this is very important, potential energy in terms of the force of gravity as we're talking about it here. The variable force of gravity, right, with big G, gravitational constant in here. Okay, so we need to know potential energy in terms of gravitational force because we need to know about things like escape velocity, and that's where it's going to be very important. But we need to get this in terms of this. How in the heck do we do that? Well, it turns out it's not that bad. Okay, so first off, if you remember what a general force is, okay, a force is a mass times an acceleration, right? And the acceleration on the surface of the Earth is g, right? Gravitational acceleration, 9.81 meters per second squared, negative, right? So that's our force of gravity on Earth. So, okay, let's do this. This is already built into the potential energy formula, isn't it? So I'm going to rewrite this in terms of force of gravity, okay? So potential energy, what we already know is it's just the force of gravity times the height above the surface that you raise the thing, whatever surface you're talking about. Again, you can set zero in a lot of different places. For us, it will eventually make sense, and you'll see why in the next video, as to why we want to set potential energy, when we're talking about orbits, potential energy at zero at infinity, way out far in the distance, okay? So for force of gravity, we plug that in here. Now let's go ahead, and now we got this here, here, and here, right? Let's go ahead and sub in. We love substitution. I know you guys love substitution, so let's go ahead and do that, all right? So instead of force of gravity here, I'm going to take, instead of mg, like we figured out before, that's what the force of, gravitational acceleration, force of gravity is on the surface of the Earth. But it changes now, we know, as we go farther away, or down into the center of the Earth, right? Either way. So, if we want to know more generally what potential energy looks like with a changing force of gravity, we got to sub this in. Okay, so we'll get little m, mass of you or whatever object you're talking about, mass of the Earth, right, if that's the way this is going. Little mass, big mass, constant here, gravitational constant, over the radius away from the center of mass, or the distance between the two objects, depending on how you're setting it up, squared. Okay? That's your force of gravity. Now we still need to have a height in there, but a height in this case, if it's you standing on the surface of the Earth, right, your height here would actually be the same as the radial distance from the center of mass of the Earth. So that R value would be your h, okay? So instead of h, we should still be talking about the radial distance between things, all right? So it turns out we got to multiply that out over here. Force of gravity times that height, okay? But now you can immediately see one of those r's cancels out, doesn't it? So potential energy with a variable force of gravity, there it is. No big deal, okay? So there's your potential energy in terms of gravitation, okay? We're going to set that equal to infinity, or sorry, zero. We're going to set that equal to, oh my gosh, potential energy at infinity, we're going to set equal to 0 joules. How's that sound? That's a little bit easier to say, right? Apparently I can't see anything. So there you go.